Hello everyone. In this video, we will try and uncover the very familiar concept on Unix and Linux circles, which is everything is a file paradigm. What does it really mean? Well, before I delve into it, I should ask you, what is a file? Well, many of you know what a file is. We all deal with files on a regular basis on a normal computer, right? Well, be it you're using Windows or Mac OS or even Linux. We store files, we create files using a text editor, or maybe compile programs which generates executable binaries, or we can also represent files which are stored on a cloud, let's say on a Google Drive or Dropbox or any other cloud storage service, or maybe on a localized remote storage. Maybe if you have a network file system server, maybe a Samba server or an NFS server, you could actually get files from there, right? So we all represent these files that we deal with there on a regular basis as some kind of persistent storage, an abstraction for persistent storage. What I mean by that is we store data onto a disk, be it a pen drive or SSD or network or cloud, so that you can retrieve it later using that file name or the file path. That's where we have these folders and the entire file system in play. Now, all the files that we regularly use, these are representation of persistent data. That's what it is. In Unix, not just the persistent data is represented as files, but most devices were also exposed as files. We know them as device files. We'll talk about that with some examples in a while when I talk about in Linux. Linux transcended further. It took it one more step further. And if you ask me what is the definition of file on the perspective of Linux, it actually means this. On Linux, a file is a user space ABI abstraction to a kernel managed resource. Yeah, I just worded it from the presentation. What does it mean? I should now break all of these terms one at a time. I'm sure many of you know what is user space here. The applications that run on top of the kernel, trying to access kernel's features and uses the kernel to perform some activity. These are the user space applications, the things that run in the user mode, the programs that run in the user mode, that is. Now, if a program has to communicate to the kernel or try to get some details from the kernel or try to access any device or any resource that the kernel manages, then the way it can do so is by two possible ways. One is an API, the other one is ABI. So what is API? What is ABI? I'm sure many of you would have heard about this and would know it, but just a quick recap. Well, if you look at from the perspective of Linux kernel, an API, what it means is application programming interface. This is basically this. The kernel has a set of functions. And these functions, the kernel wants to expose to user space, such that an application can invoke those kernel functions. The way the kernel does it is by an API. And the APIs for all Unix and Linux are also called as system calls or syscalls for short. For example, if I want to open a file, I use a C library function called open. Some of you might think, oh, I use fopen. It doesn't matter whether you use open or fopen. What are these functions? These are technically C library functions. Some of you who did some systems programming on Linux would know that open is a system call. Open is not really a system call. Open is a function that wraps a system call, technically. So when I use open, read, write, close, dupe, socket, or fork, execve, all these are system call functions. This syscall functions, all of them, they take in the parameters that you pass, fill them up in some of the CPU registers, sometimes on stack, but mostly on CPU registers, and then they invoke an instruction, a special instruction called the syscall instruction. The syscall instruction raises a trap. What exactly is a trap? I would have covered that when I talked about the user mode, kernel mode concept in the earlier video. I recommend you go back and watch the video if you're not aware of traps. Traps, in summary, I should tell you, is a means by which kernel gains attention when the user space performs certain things that is out of its protection, right? For example, if a user space program tries to access illegal memory, or it tries to perform perform a divide by zero, or it tries to run an illegal instruction. All of these raises what we call as a trap. And this takes the attention from the user mode to the kernel mode. So the kernel's trap handlers get executed. That acts as the entry point for the kernel from the user land. Now, amongst all the different traps, there's one trap called syscall trap, a trap dedicated for system call. The user space just wants to nudge the kernel to do certain things. It'll trigger this trap called syscall trap through this syscall functions, which I just talked about a while ago. And these syscall functions, when they invoke syscall trap, the program counter or the instruction pointer hops from the user mode, from that application, into the kernel core, the entry point of the kernel, which is the trap handler subsystem, right? And the trap handlers will figure out what is the trap code number by looking up some special registers on the CPU. We call them as the trap registers or trap status registers, or different terms used by different CPU architectures. And these registers will have a trap code number, different trap code number for different kinds of traps. And one such trap is syscall trap. If it sees if the kernel figures out that the trap is for a system call, then it calls do syscall function, and do syscall would basically look up a table, which is nothing but an array of function pointers called syscall table, uses a system call number that is there in one of the registers, the first register that is, as an index in that table, in that array, technically. And that index is a function pointer. It invokes that function. That's a kernel function running on behalf of the user space request. So this is how APIs are implemented. So open, read, write, close, fork, dupe, all these so-called syscall functions that we use on Linux, these are kernel API. But then the kernel on Linux, the Linux kernel that is, would expose a lot of or a variety of resources it manages by another technique. We call it as ABI. And ABI stands for Application Binary Interface, like you see there, right? As you can see on my presentation. So what is an application binary interface? Well, this is a mechanism where we use some standard API, a standard set of APIs, like say a few set of APIs. I would say that, let's say open, read, write, close, 4 APIs, right? 4 functions, open, read, write, close. The same APIs can be used to expose different resources based on the parameters. For example, if I open one particular file, the kernel will expose one resource, which you can access by reading it. Or if I open another particular file, the kernel can expose another resource, which I can read. Or maybe sometimes I can even write to send data to the kernel. So this is what we call as an application binary interface. Now, basically the kernel, a variety of kernel managed resources are exposed to user space as files, as if they are files that can be manipulated by using all these file system related calls like open, read, write, close, ioctl, fcntl, and many other functions which deal with files, right? And these are what we call as the kernel ABI. Now this might look very theoretical, and you should note that Linux has a very fat ABI at the moment. A lot of kernel features are exposed as if they are files. When I use the word as if they are files, that means that those files don't really exist on your storage. They're not stored on disk. They're not stored in memory. They're not stored anywhere. They make us believe there are files in some folder in a path, and the moment you try to open them using open function, some callback handlers get invoked. The open function will figure out, oh, you try to open this particular file, so let me call another callback handler, which the kernel is implemented. The kernel drivers and subsystems would do that, would have implemented callbacks for different kinds of files, and those callbacks will work differently for different kinds of files that we're dealing with, which actually means that the number of functions that you need to know to leverage various kernel features, very few functions, just that the arguments that you pass, that will vary. That will determine what resource you're interested in. Now, showing you all the theoretical concepts might look very abstract. So let me show you some practical analogy with examples. Now let us assume that you want to record or playback audio on Linux. Before Linux, let's say on any other operating system, like say a Mac OS or Windows, how do you do that? Well, in fact, to record audio, you need a program or an application for recording voice, maybe a voice recorder or an audio recorder. You install the software and you run the software and it'll do the job. That's what it is for end users. But if you're a programmer and if I ask you to write a program to record audio, what do you need to know? You need to know about what we call as sound APIs, right? So if you're on Windows, I think it is called Direct Media API. I'm not a Windows developer. I'm just trying to word it. So in Windows, will have its own sound APIs. Mac OS will have some core audio APIs. So those are functions, specific functions, which will hook onto specific functions on the kernel. So all the sound functions with the kernel are exposed to userland, and the userland programs can call them by syscalls, of course. If I want to access my mouse events, there's a specific API for managing mouse. So that's how it is on all your everyday operating system. How do you do this on Linux? How do you record or playback audio? Well, here's a small demonstration which works on the machine that I'm using with a kernel that I have built. This may not work on your regular Linuxes. I will tell you the reason why in a while, okay? But for now, just watch the demonstration so you'll understand the core concept in here. Let us say I want to record audio on Linux. All I need to know is to use cp command as an end user. As an end user, I don't even have to install any software. I can use cp command, good old cp command, and then type in /dev/audio, and I'll provide another file, let's say test file.dat, or maybe I'll call it as myvoice.dat, enabled. And when I press enter, one thing you note about cp command is it's a command that uses open, read, write, close primarily. There are other functions it uses, but these are the major system calls, right? So cp command is given two arguments. The first argument is /dev/audio. That file is open for reading. Another argument is myvoice.dat. That file is open for writing. The cp command is going to keep reading from this file called /dev/audio, and whatever data it reads, it's going to keep faithfully writing into that file, myvoice.dat. And you can also see that files can be treated as streams. You've heard this term called IO streams, right? So what we say streaming IO. What does it mean? Well, just like a stream, river stream, or maybe if you're at home or your office and you go to a water dispenser and you open up a tap to dispense water. The tap gives you, there's a flow of water. There's a water stream flowing from the tap, from the water tap. How long does it flow? Until you close the tap, until you decide to close it, cancel it, or until the tank that holds water runs dry. But here's a stream that when I'm reading it, it does not run dry. It goes on forever. It's very likely like it's, imagine you have a 24/7 water supply and you left a tap open at your home and you're not present. For all you know, your house can get flooded, right? That's what is happening right now. So it's taking data from /dev/audio and writing to this file. So we can just verify that. I'll just say Control-C to cancel it now. That's how I close the tab. And now when I look up this file, ls-l and myvoice.dat, as you can see here, this particular file has accumulated some data. There's a size here. The size shows up some 524288, some number. It's got some data. That's why it's got some size. Now let's do the reverse of it. I'm going to do a cp myvoice.dat to /dev/audio. And I'm going to stop speaking, but still you'll hear my voice coming from here. And you can watch me. I'll be silent. One thing you note about cp command is it's a command that uses open, read, write, close primarily. There are other functions it uses, but these are the major. All right, I'll stop here. Right? As you could have heard, I was able to play back and record audio by using simple cp command. I don't have to install any software, isn't it? Isn't that great? Well, in fact, this is a core principle of trying to treat an audio device as if it is a file. This is nothing new to Linux. This has been predominantly on Unix environment. A lot of devices were seen as files on Unix, and we see them as device files. We have character device file, block device file, which I'll talk about much later, in the much later video. But for now, we use this term called device files. Devices are also files, right? In fact, I showed you how to copy a file by using copy command, but some of you write a C program. How do you do it? Well, you just need to open /dev audio. You get a file descriptor. You do a read on that particular file by using read system call on the file descriptor into a buffer, and you're recording audio. And then you can store it somewhere, maybe by opening another file for writing and writing it there, and that's how you can store it. And your playback audio, you open the same file /dev audio for write mode, and then you start writing to it. The audio gets played back. It works like magic from the user land, right? But this is not all. You can see a lot of other examples. For example, I showed you with audio. And I should also tell you that this example which I showed you, if you write on modern Linux, all the mainstream Linuxes today, they don't work by default. Most kernels, they would have disabled this. You might ask me why. The reason is because though this looks good, it's good for beginner to understand this concept of ABI. Many device drivers don't just expect you to just open the file and start reading it. If you had heard my audio, it was not very clear. It is not like what I'm speaking right now. The audio was a little like speaking on an old telephone, right? Because it was the sampling rate for recording audio and playback was 8-bit. How do I change to 16-bit or 24-bit or 48 bits? Well, there is no easy way to do it. Because open the file I'm trying to read. How do I increase volume, reduce volume? Or if my sound card is quite capable, I want to do some graphic equalization of my audio. All these things cannot be simply achieved by using open, read, write, close semantics. One of the ways these can be handled is by using something called as ioctls. Ioctls, we call them as IOCTL, generally pronounced as ioctls, stands for IO control. If you have opened special files, like device files, apart from reading and writing from them, you can instruct the kernel to handle things more differently by using ioctl system call. You can send some ioctl commands, we call them. IO control commands. And these commands can mean increase volume, reduce volume, or change the bit rate and all that. And the current interface I have, this is called as Open Sound System Interface. Even today, if you're building the kernel, if you're custom compiling the kernel, you do have an option to enable OSS support or ALSA OSS support, and you get this file, /dev audio. The standard Linuxes don't do it because they have an alternative approach to deal with this. Instead what they do is they provide a more raw interface. That means if you just look up /dev/snd folder, you'll find a lot of files in here. Like you have this PCM C0D0C, PCM C0D0P, then you have some control C0, HW C0D0. So each of these files gives you different features of the sound card. Rather than exposing a single file called /dev audio, which only gives you raw audio access, I want to get the sound card's capabilities. I want to know what are the capabilities of sound card. Or I want to, let's say, control the sound card. I want to change the bit rate. I want to permanently set the bit rate for the sound card to something. All these are possible by working with different files. Because there are so many files here, managing them manually is quite difficult. And most of these files expect some binary data to be sent in a particular structured format. Your cat command or cp command will not work on this case. But still, they have exposed the sound card as a file, sound device as a file. But to manage them, they have provided their own tools. And this interface is called as Advanced Linux Sound Architecture, or ALSA, which is popularly used for audio right now. And this architecture provides more fine-tuned or fine-grained ways of controlling a sound card and managing it from user land, right? Not just open, read, write, close. They provide more features by working with different files. And to manage them better, they expected you some of these ALSA utility tools. Like for example, if I want to record audio even now, I can use this command called arecord, which comes with ALSA utils or ALSA tools package. And install the package, you get this arecord and you play. So using this command, instead of your cp or cat command, you can use this. This will take care of working with multiple files, not just one. It can open one file to get to know the sound card capability. Then it'll work with another file to set a control command for it, and then read the actual audio stream from the other file. So that's how they work. They all do file IO internally, but they have provided a library called libalsa, which abstracts this with some functions and API, and tools like arecord and aplay use it. This is becoming the norm these days on Linux. Though the kernel exposes resources as files, they expected you some plumbing library functions which provide API for actual applications to work on for sound card and so on. The kernel interface is still simple, but a lot of the function complexity is embedded now in the library layer, right, of the Linux stack, which you got. And this particular command, I think I don't remember the switches, so I'm just going to use a record ----help pipe less, and maybe I need to list all the devices first. I'll use list PCMs rather. I'm interested in raw audio access, so I'll use a PCM device. I can use a record -L, choose a PCM, and from there use the capital L. This will try to get the capability of my sound card, listing out all the sound devices that I can use and features I can use. From this, I'm mostly interested in my actual sound card, which is, I could use maybe default. I think default will do. I think I can just use this generic audio device, right? I can use this on my VM. So I could use a record, and I can select the device as this particular device. And then I can also use another feature. Let's say I need to also set the bitrate. So let's try this. First, I can say a record -D, and I can just type default. And I can provide a file name, testdata.dat. Oh, it says invalid duration argument. It's not duration. It's not -D, I guess. It should be -D if I'm not wrong. But I can see that it's recording in 8-bit. If I want to switch it to 16-bit, I should use a -F and 16-bit audio. I can even do that. I can try -F, and I can just type yes16_LE. Use 16-bit sample rate for the audio. Let me make it -F. I misspelled it. This time what I'll do is I will also run a tool called strace. If you're not aware what strace does, strace traces the system calls invoked by any program. If you have any application running, you want to trace the system calls, you can use strace utility. So if I run strace here, I want to store the output of strace to a file. I'll call it as a record.trace, and I'm going to run this command. Oh, it says open error. Okay, it looks like -F. I made a mistake here somewhere. Increase resolution. All right. Looks like I put a S16LE. I did that. Okay, let me leave the default. Doesn't matter. 8-bit, fine. It's okay. Maybe the argument must be passed in a different way. Oh, I put a -D after that -F. That's wrong. I should be -F S16LE -D. After -D, it should have file name, right? So that could be a problem. So right now I'm just speaking some words, and you can see that it's getting recorded at this moment. So let's see how much of recording I've got right now. I just type Control-C right now, and you can look up this file called testdata.dat, and you can see it's accumulated some size 176,164, as you can see there. Now the point is that if at all I want to now play this back, I can use a play. I'll use strace for this also. Strace -O, a play.dat, and I'll type a play, and I'll provide this particular file, testdata.dat. Maybe the argument must be passed in a different way. I guess. Oh, I put a -D after that -D. That's wrong. I should be -F S16LE -D. After -D, it should have file name, right? So that could be a problem. All right, I'll stop here. Basically, you can see that I'm using the tool called a record and a play to record and playback audio. And if you look at the system calls they invoke, these are being stored in the trace file. I put a strace -O to store all the trace into a file. Let me just open them up. Let's look at a record.trace. You see a lot of system calls for program loading itself. This program is a shared library executable, so you'll see a lot of shared libraries being loaded. All these calls are the C boilerplate that you see there. The loader stub, which you call. It reads certain files. You can see that alsa.conf and other files. And what I'm interested in is, yeah, is there a file that is of importance? Let me just look up. It is a lot of configuration files to begin with. And yeah, you see this right here. This particular entry. OpenAT, ATC, ATFDCW. OpenAT is the modern implementation in the kernel for open system call. So when you use open C library function now, it is a wrapper on OpenAT system call these days, right? So it takes another extra parameter indicating what is the directory where you want to open the file on. So directory argument is passed as first parameter. Open takes care of doing that. And you can see the file is being opened. It opens a control file for reading. And then it sends some ioctl. There's an ioctl system call on this file descriptor. This file descriptor number 3 is the return value of open. Open return file descriptor number 3. And that is used as a parameter ioctl to set some control, getting the card information, I guess. And then after that, it tries to do some validation with alsa.conf. And then again, it opens up this particular control file one more time. This time it sends another, okay, it tries to, I think, looks like it enumerates variety of cards, I guess. And then ultimately, it figures out what card I have, and based on that, it reads a configuration. And then somewhere down in this crowd, you'll see that it opens up that particular file from the device. Okay, you'll see /dev snd somewhere down. Okay, all these are reading config files, but then, yeah, I can see this file is being read. A lot of these files are being read. It tries to read this file. It looks like all these files don't exist. Tries to enumerate them. Looks like these device files don't exist for the sound card, so they're all failing. But somewhere down, you can see that it again reads control 0. It does a lot of these reads on these device files to enumerate the sound card and find out what sound cards you have and validate it. And then ultimately, it tries to send data to that sound device. That's how it works. If you read through this trace, you'll find it, right? Or capture data from the sound device. In fact, if you look at even aplay, the same story. Look at aplay also. Tries to work with /dev snd some file, right? Which will be like control C0 or PCM C0D0, whatever that name is. So look at aplay.trace. When this, okay, I think have I recorded it? Okay, I called this .dat. Sorry, .dat. So I just search for snd. Quick way. Yeah, you can see that it opens dev snd0 just like earlier. It does all these control similar to a record. Let's search for PCM. Yeah, I can see this. This is where the actual write happens. Writing to sound device when you play it back, right? It opens in read-write mode. And after that, it sort of sets some ioctl to get information about it. And then a couple of ioctls are done. And then it actually controls it. Sets all the controlling activity. And then ultimately, it would send it. Right? That's how you see this works, right? So in fact, this is an example of sound card. Modern sound cards are implemented this way. But if you want to use simple old school mechanism, I think you should just custom compile your kernel, or if you're lucky, the kernel that you have might have that driver built in as a module. You should just load that module. It'll generally be called as sndpcm OSS. So you just load that module and you get access to /dev audio for it to play around. But sound is just a simple example. Let us say I want to get information about mouse movement. I want to track this mouse movement information. So what do I do here? This is also a file. So if you're using a graphical user interface like your X Windows system or Wayland or any kind of graphical desktop on Linux, how does that graphical user interface figure out where the mouse coordinates are and what button I pressed and all those details? It reads a file. And in my machine, that file happens to be a file called /dev/input/event9. How do I figure it out? There's one tool to find it out. If you have a tool called ls hardware, lshw, it lists all the hardware details. From here, you can look at the last entry. IMEXPS2 generic explorer mouse, input 4. It is available under the file /dev/input/event9. This is also a file. When you try to read this file by doing a cat is a bad idea because it will print binary data. Terminals can get messed up when you print binary data using cat command. If you plan to use cat command, use cat -A switch, but I'm going to use xdump. If you want to read binary data, the best way on Linux is using a command called od or xdump. Od is octal dump, found on many Unixes, available also on Linux. The modern avatar of it is hexdump. You can use hexdump and you can do a slash dev slash input slash event 9. Right now it's like blocking. It's like waiting for input to arrive. Now the mouse movement here would not matter because I'm running this in a VM. So I should go to the VM console, which I have opened in this place, in this window. This is a VM console. When I select this console and when I move my mouse inside, so when I move my mouse, you can see a lot of binary data being printed there, right? A lot of binary data from Mixed-up. So this is all based on mouse movement. The mouse is moved left, right, up, down, press the left button, press the right button, scroll wheel. So all of these activities which are performed on the mouse shows up as some events in here. This event interface is also a very, very interesting one. Almost majority of the input devices, be it mouse, keyboard, joystick, tablet, touchpad, all of these devices have a very similar interface. And this is again an ABI, which means that if you want to get mouse events, just open this file and start reading it. But only thing is that you'll not be able to make sense by using standard Unix utilities easily. But I wrote a small C program to demonstrate what kind of data I get in this case. So I'm going to use that program. Let me just unlock my mouse from here, go back here and say Control C. So I've written a small C program called read input events.c. Under a folder called /dev/input, you'll find a lot of files called event files, event 0, event 1, event 2, event 3, and so on, depending on all the different input devices that you might have. And all these devices, where you can capture what events are occurring on those input device by reading this file. A key press or a tap on the touchpad or multi-touch gestures or, mouse movement. So all of these are events, technically, input events. In order to capture the input events, they expect you to write a C program or maybe any program in any language that allows you to have this kind of a structure. I've created a structure here in this main function in C. I have a struct input event struct. I just named it this way. Whatever the name the structure is, doesn't matter. The only thing is that the structure has these elements. So whenever there's an event, it sends a record of these data. There's a timestamp followed by a type code, followed by a type, followed by a code, followed by the value. Depending on the context, if you opened an event file representing a keyboard, the type might indicate whether it's a key press or a key release, and the code will indicate what kind of press scan code, release scan code, and the value might contain any data, like scan code itself could be repeated. If it's a mouse, it might also tell you whether the mouse movement, whether it's moved, whether the mouse had a movement, or whether it's a button press that could be represented by the type, and the code will tell you exactly what is the absolute or relative position of the mouse X and Y coordinates. So those details are embedded in code and value. So it varies based on what kind of input device you're dealing with. So what I'm doing in the C program is I just created the structure, and this program is very simple. Yeah, it's a C program. It's got a lot of lines, but of course, code is very simple. I'm just trying to open a file passed as the argument, and I'm using open function here, right? And it returns a file descriptor. I'm doing all the validation here. It's possible that I give a wrong path and the file could not be opened, or maybe I don't have permission on it. So all these reasons, I'm handling that part. And if the file is opened successfully, what I'm doing is in a loop, which never seems to end, which will never end actually, it's going to do a read. It's going to read from this file descriptor. As you can see, it calls read on FD into that structure. I have created a variable called input event, which is of type input event structure. It's going to read it into that structure. And once I read into the structure, I get all the elements, the timestamp and the code and the type and the value, all of these details I can get from the structure, and which is what I'm printing using simple printf function with some nice formatting, perhaps just like Xdop. I'm just doing that here. And this goes on forever in the loop, because every time you do a read blocks unless you open the file in non-blocking mode. It'll block. So it blocks, and once it gets a record, it returns a record, which is in this structure format. And this structure's details I'm printing, because this data being read will be size of structure. It'll never be lesser. So this will go on forever, right? But anyways, so I'll just run this program and I'll show you. I'll just compile this first. Now when I do this, when I actually do a cat Oh, not yet. Sorry. Run this program. Sorry. Read input events, and I'll try /dev /input /event9, which happens to be my mouse on the VM. I'll go to the VM again, and I'll try to make some mouse movements while I have selected this console. I'm moving up, moving down, moving left, moving right, press the left button, press the right button, turn on the, rotate the scroll wheel. So you can see each entry shown up as some couple of records, right? So let me just tap this and come back here. These could mean a lot of things. I mean, you can look at the X and Y coordinates and relative position, scroll wheel up or down, how many rotations, all those details you can get from here. In fact, to make things easier, there are libraries to handle this, and these libraries will give you more detailed insight. In fact, there's a userland diagnostics utility which uses the same library. It's called as libev. Okay, lib input, I guess, lib input or libev input. So this library, there's a program that uses it. In fact, you can install that by using on Arch Linux. You can install by using pacman -S and evemu, event emulator. It's already installed on my computer, right? I'm just going to anyway proceed with installation. Now, when you have this particular package installed, you can use this tool called evemu, and there are a lot of files in here. For example, if at all I try evemu event and give a path to the file /dev /input /event9, this does the same thing. It sort of reads this file. Oh, okay. I need to, it's not event, I guess. Sorry, I should not event. I should say record. It will record all the events. The second one will trigger an event. Sorry. The keyboard is in the wrong place, so I'm struggling with that. Yes, waiting for events. When I go back into this particular console, move down, move up, left, right. So it actually gives you a very nice commentary along with that binary values. It also prints in a nice commentary on what exactly this event or type actually means, the type and code, what they actually refer for a mouse, right? So you can get that details in here by looking at this annotation. It tells you the X movement, Y movement, where is X is moved relatively, and all the details, right? X and Y coordinate movements, which you can see here. In fact, I can access even keyboard events by using event2 on my computer. Actually, when I run lshw, event2 shows up as my keyboard. So I'm just using that over here. It's going to look up keyboard events. When I go back into this particular terminal here, the console, I'm going to press and release a key. Press A and release A. Press and release. I'm going to press S and release S. Press and release S. Press and release D. Press and release F. So you can see that these events are also recorded. The program that I wrote, if you read it, you'll get in raw format. Only those numbers is what you get. What those numbers signify, this is annotated by this tool. So they all mean different things, right? It shows very clearly that I pressed A and released A, press S, release S, press D, release D. You can see the complete details, right? So the point is that if at all you want to work with keyboard, mouse, touchpad, and all these things, you just need to work with files. From the kernel's perspective, they're all just files. So devices as files is a very common phenomenon that is popular on Unix and Linux. The last example I want to show you is something more interesting. It's got to do with the IoT boards, right? Today we know that a lot of Linux deployments are on embedded devices like the single board computers. I'm talking about Raspberry Pi and family, right? Raspberry Pi and alike, I would say rather. Raspberry Pi, BeagleBone, Latte Panda, all these devices. They are quite popular. And Linux is the most commonly used operating system on these devices, right? So if at all I want to show you a small demonstration on working with the Raspberry Pi board, I have let me just bring up my desk camera here. I hope the desk camera is visible. All I have here is a Raspberry Pi Zero, which you can see here, right? So I have a Raspberry Pi Zero, which is a Pi Zero WH model. And one of the interesting things with the Raspberry Pi boards is that they have this GPIO headers, which you can see the soldered headers in the back. And to make things easier, I have connected a ribbon cable on these GPIO headers, and I'm using an expansion board here which I can lay it out nicely on a breadboard. And the expansion board is a very convenient way to look up all these GPIO pinouts without looking through these pinout manuals and reference guides. So it's very easily laid out here. What I've done here is I've connected an LED, right? A simple red LED through a dropping resistor to one of these pins, which is GPIO 17. I've connected this GPIO 17 in here, right? To a dropping resistor to a red LED, which goes to the ground. You can see that the 3-volt supply and the ground is connected on these rails on the breadboard, and you can see the LED is connected. This is connected to a pin called GPIO 17. And I also have a small touch sensor, which is like a toggle switch. This is a capacitive touch sensor, which I have. Again, this got just 3 pins. And yeah, one of them is the VCC pin, which is connected to the positive rail here, and the ground pin, and the output pin of this touch sensor. I've connected it to GPIO 23. If there's a wire that goes from the data, I'm sure you can see it, yeah, from the data to this location. And then from GPIO 24, I've connected to another device, which is apparently a distance sensor, so also called as a line sensor, so which actually finds out at what distance I am in, right? If I'm in line, it sort of figures it out. It's a line sensor, not a distance sensor. It's a line sensor, right? It just checks whether there's an obstacle in front. Mostly looking at obstacle sensors, I think that you can use it. It uses an IR and a sensor for matching it. It's a small logic circuitry, which is connected to GPIO 14 with the VCC and ground pins connected. These are very simple devices I've connected to GPIO pins, GPIO 17, 23, and 24 on this board. Now, with this being done, I want to, let's say, control this, right? I want to control this. In fact, to control this, what I'll do is, okay, let me just, for now, come back to the terminal. Then I'll switch back to this camera. Because I connected on a Raspberry Pi board, I'll need to connect to a Raspberry Pi machine here, which is connected by SSH here. I hope it still works. Yep. Now these GPIO pins which are connected, the GPIO 17, 23, 24, all these GPIO pins, these are also like devices. Not in the latest builds of Linux and not in the latest versions of Raspberry Pi OS. I have a slightly older version of Raspberry Pi OS to demonstrate in this case. So these files are also exposed under /sys file system. Under /sys class GPIO, you have them available. The entire GPIO controller related information is exposed in here. This is a little peculiar because if you treat this as a device, you should ideally see a device file. But in the early days of Linux kernel, they exposed GPIO as files under a pseudo file system known as sysfs file system. Sysfs, anything that you see under /sys is a mount point, official mount point for sysfs file system. Okay, and whatever you see here, none of them are stored on disk. None of them are persistent. These are all various kernel resources being exposed, mostly device related information, core kernel diagnostics information, some device diagnostics and subsystem diagnostics, and debugging information. So a lot of details you'll find in here. In fact, this has become a bigger forest now. You see a lot of other pseudo file systems mounted underneath. You'll find them under /sysfs, by the way, like C group file system and, you know, boot config file system and so on. So anyways, that's for a topic for another day, another video. But for now, let's focus on this particular path, /sys/class/GPIO. Now, the beauty of working with Raspberry Pi with this interface is you can just use simple shell scripts to control these GPIO pins. Let's say I've connected an LED to GPIO 17, which I just showed you in the disk camera. And that is to be set as an output pin. The way I do that, first, let me expose that pin. I just type echo 17. Okay, I had already exported GPIO 24. Let me unexport it for now. I was doing some tests before I actually started the video. So I'll come back to it. Normally, when you look up the entries of, I'll just go to this folder, /sys class GPIO here. I think the echo 24 unexport. Okay, I think I put it on unexport in the wrong place. Sorry. It's not in the path. Let me rerun this command. normally when you go to the sys class GPIO the first time, you only find some 3 files, like you have file called export, GPIO chip 0, and export. There's one GPIO chip controller chip on the Raspberry Pi 0. That's what is shown here. So if at all I want to expose a pin that I can control, I can just type in the pin number, like say echo 17 greater than export. And now when you run ls command, you can see a new entry called GPIO 17 that comes up. It was not there earlier. I didn't create this file. Well, the kernel created it. Is that so? The kernel just makes this GPIO 17 available to me as if it is a file. That's what I mean by using the word abstraction here. So you should note that this file is not stored anywhere on disk. It's not stored anywhere in memory. It is merely a kernel data structure being abstracted as if it's a file. Technically, it's not even a file, it's a folder. You can see that. -ls -l actually is a symlink to a folder. It's a symlink to another folder. I can just look up the contents of it. This folder has a lot of entries. Most of these, all of these are files, mostly. And what is important in here is first I need to set this as an output pin. For that, I need to set the direction as echo out greater than direction. I should type GPIO 17/direction because I'm in the top level folder, right? Echo will write to that file. I just redirected the output to this file. So I set this as an output. And now I can do one thing. I can just say echo 1 greater than GPIO 17/value. Well, let me bring up my disk camera at this moment. As you can see that the LED is glowing. So while the LED is glowing, what I'll do is, okay, I will try and see if I can bring this terminal more towards the right side. All right. Maybe as much to the extreme right. Yeah, let me just clear the screen. So as you can see that when I did echo 1 greater than GPIO 17/value, the LED is glowing, that you see here. If I want to turn off the LED, all I can do is I can just type echo 0 here. And yes, the LED stopped. So maybe you want to implement a blink program. You can just write a shell script while true, bash script, that is bash or bourne shell script. I can just type maybe echo 1 greater than GPIO 17/value and put a sleep for 1 second and echo 0 greater than GPIO 17/value and add a sleep 1 again. And as you can see, I wrote a simple blink program as a shell script. The beauty is that I was able to control this GPIO pins just by doing some file operations. All of these are file operations, right? I'm just opening a file, writing something to it, opening a file, writing something else to it. So this is how it is. You can also use it as input device. Like I have this line sensor and the touch. Both of these are inputs. So if you want to read them, you can also do it like this. You can, let's say, echo, let's say pin number 23 to export. And now I'm just going to do a watch cat GPIO. First, I'll make it as an input pin. First, I'll do that. Let's say echo in greater than GPIO 23/direction. Making an input pin. You write out to it, it becomes an output pin. Otherwise, I can make it an input pin. That's what GPIO is, general purpose IO, right? You can actually configure it as an input and output and implement any protocol by bit banging on them, right? All that can be done. And I'll just do a watch cat and GPIO 23/value. I'm just going to watch the value. You can see the value is 0. And I can just see what happens when I tap on this button. It became 1, right? It just turned to 1 there. If I tap again one more time, I can see it's 0. It's 1 one more time, 0. So as you can see here. So I can actually work with this touch input. Or the same strategy can be used with even the other device which I have, which is an obstacle sensor, it's a line sensor, right? So if at all I want to export that to, I can connect this to GPIO 24, and I can also make this as an input pin. And then watch this file too. Right now by default it shows 1. I think you need to, if you can see what happens when I move my hand closer to this. It became 0. Move my hand away, it's 1. It's 0 now. It uses a technique called active high. If you want to convert to active low, all I can do is I can further configure this by doing echo 1 greater than GPIO 24 / active low. Another file. And now when I watch this one more time, it shows 0 by default at this time. When I move my hand across closer to the sensor, you can see it shows up as 1, it's detecting the obstacle. When I move my hand away, it becomes 0, right? So you can see the example of how we can treat variety of devices just by using file operation. And this is a great thing. And yes, this is, I told you, is not unique to Linux. This is the old Unix ideology that is carried into Linux. But Linux, I told you, took it one more step further. It is not just that devices are files, but you can see that just about every kernel managed resource is a file. Now I'm going to show you what is unique to Linux, which is not found in many other Unix and Unix-like operating systems. You can compare it with FreeBSD or macOS or Solaris, and yeah, Solaris has a very limited support for this feature I'm going to talk about. Linux is like a superset in this feature. I'm going to explain that. So let me just bring back my terminal here. And yes, we don't need the desk camera anymore. So I'm just going to Control C out of it and go back to my terminal here. All right. If not, I want to find out memory statistics on my computer on Linux. How do I do that? Well, the standard command that people use on the command line is a command called free. Or some of you might use top or htop, which also gives you the memory statistics, right? How does these tools get these details? Well, one way to do it is maybe invoke a special system call into the kernel called getMemInfo or getSysInfo or something like that. And maybe sysinfo of get memory details or something. And the kernel could return a structure and that could be it. But you know how it's done on Linux? I can run strace on free and show you. Let me run strace -o. Oh, okay. Fine. I'll just come back to my home directory. Let me not clutter my samples. Strace -o. free.strace. And then free. Or free.trace if you want to call it that way. The free command just executed, but what system calls that the free command invoke? If you want to note that, just look up free.trace. And in here, of course, all of these initial system calls are for the program loader itself. That is your C runtime begin stub and the loader, right? The dynamically linked program loader. So all that takes care of loading the C libraries and all the other shared libraries that this program depends on. The main boilerplate starts somewhere around here. The main function starts somewhere around here below. All the way down. No, not here, not here. It's on top. Yeah, you'll see some signatures like set TID address and set robust list and RSEQ and a couple of mprotects, and that's where the main function starts. Somewhere around this region, right? After the system call. And you can see that. Try to open a couple of files, I guess. Did it? No, not yet. Yeah, but yeah, it's trying to open some locales. Okay. But the more important part, this one. Open at /proc meminfo. It opens this file for reading and it gets a file descriptor number 3. 6 to the beginning of this file descriptor by using lseek system call, and after which it tries to read data from this file. It tries to request the kernel to read about 8 kilobyte, roughly 8 kilobyte word data, but looks like the file only has about 1.3 kilobyte word data. That's the written value of read system call. How many bytes being read into the buffer. And whatever is being read, that is what is printed. By using the current locale, it prints the details on standard output, right? Which is again a file descriptor number 1. Now the point is, if you know that free command uses /proc meminfo to get the details, can I read that file directly? Let's try it. Yeah, we got the entire details in text format. Not even binary, right? Not like the event file which I showed you, which is in binary format, which I'd read. It's in text format, which means that you can write a shell script or a Python program or a program in any language to read this file. I'll tell you why this is so crucial. Take this as a problem exercise and see solving it. Try writing a program in a high-level language like Java or Flutter or JavaScript. You know, all these are like the high-level languages. They are very far off from the operating systems. Java is a platform-independent language. But how about writing a Java program to get memory statistics like these? I want to find out how much swap is used, how much swap is not used on my computer. Can I do that? Or maybe find out total memory and how much memory is available, how much is free. Yeah, if you are a Java developer, some of you might tell me that, oh, just a java.runtime or java.lang.runtime that has this get total mem, get high mem, whatever. You could use that. But what about more details like swap and how much is cached, how much is buffered? How do you get those details? Well, if you want to try this out on any other operating system like Windows or macOS, I will just say good luck, because you need to write a small C program as a library. We call it a Java native interface. Or for JavaScript, again, you need to write some extensions in JavaScript, C extensions for JavaScript or Python. And then through that extension, you read it. But how do you do it on Linux? It doesn't matter what language you use, what programming language you use. All you need to do is open a file, read from the file, and try to decipher it. So it is very, very programming language agnostic, right? So because I can read it from a pager like less or any command, like I can use cat command, right? You can write any program to read this file and use simple text manipulation. You've got textual data, you can use string tokenization or regular expressions or all kinds of string manipulation techniques and get exactly what features or what fields you want. But I just showed you one example, but it's not all. Almost most of the process related information that you get on Linux, all of these details are fetched via ABI, not API, not application programming interface, but application binary interface. That's where the proc file system plays a major role. The /proc folder that you see here on all Linuxes, this is the official mount point for a pseudo file system. Pseudo is fake, right? Pseudo file system called procfs. Just like /sys is official mount point for sysfs, /proc is for procfs. And this particular file system provides you a variety of files and folders. A lot of these core kernel diagnostics and statistics are exposed in proc file system. The traditional Linux, even some device related information was exposed. For legacy reasons, you'll still see some folders. You might see some folders like ACPI, bus, and asound and driver. These are deprecated. These are just there for legacy compatibility or some old applications which rely on these files which existed in the earlier versions of Linux kernel. All the device related information now is moved to sysfs. The device related hardware and device related information officially now is in sysfs file system. But all the core kernel features and functionality, mostly any details you want to get about the memory management subsystem or the process subsystem, are all under /proc. In fact, the proc file system originally appeared in the successor of Unix from AT&T. It was AT&T, but then it moved on to another company, Vita Nuva, whatever, and they had a ambitious project called Plan 9. It was initially called as Plan 9 from Bell Laboratories. The same people who created Unix had created a successor for Unix which failed in the market. They could not really sell it. That's called AT&T Plan 9 or Plan 9 from Bell Labs. But eventually that Plan 9, the division that was holding it, was spun off as a separate company called Vitanua, and they were working on other innovative research operating systems, I believe. But Plan 9 now is open source. It's available if at all you want to look into it. If you want to look at a very good kernel design, I think Plan 9 is a classic example to look up. An ideal kernel from the design perspective. And it was AT&T. It is a Plan 9 operating system that originally came out with the proc file system. But eventually various other Unix vendors like SunOS and IRIX and many others, they saw this feature looks good. Let's try to put that in our Unix environment. And that's how proc file system got onto other Unixes. And Linux was not left alone. But I will tell you that Linux has got the best implementation of procfs. There are some operating systems like macOS and the modern version of FreeBSD that don't even have proc file system. They say, no, that's bad. That's not good. It's complicated. It makes the kernel too complex. There's a lot of complexity involved in the kernel in Linux. The Linux kernel is in the implementation of procfs and a lot of subsystems leveraging them. In fact, on Linux system, when you do a ps command, process status or psax, you know how this ps command gets its details? Not by using any special system calls or APIs, but by navigating the contents of the /proc folder. That is the proc file system. So if I run strace and psax, you can see a lot of open. Okay, I think it just scrolled too fast. So let me just scroll up a bit. There's the output being printed. But you can see a lot of open, read, close, open, read, close, open, read, close under various folders of /proc. So when you run ps command to get process status or run top command, rich top command, or any kind of process monitoring utility on Linux, all the process details are fetched by navigating the contents of /proc that you see here. Let me show you a simple example. Maybe I can just, I think I am running on tmux. That's good. So let me launch some program that runs a shell. Let's type, let's say Python. This is a Python REPL. And now when this REPL is running, let me just also find out the process ID of it by using Python semantics. I can use import OS and os.getPID. Note that the OS module in Python wraps the system calls on Linux in Linux environment. So you can get access to variety of Linux system calls from within Python by using OS module. Okay, a lot of them. So there's a process ID of the Python shell that's running over here, the REPL, the read eval print loop. And you can see that the process ID is 4809. So let me just go to another tmux screen, and here, if I just do a psax, you can even note that the Python binary is there listed in here, 4809. How does ps command get these details? Well, there's a folder called 4809 now. Everything that the kernel has to expose in relation to this process to userland does so by this file. A lot of files in here. So one file I want to show you, which could be of interest, is /proc/4809/status. In fact, I can tell you that majority of the files are text files, majority of them. A lot of these files you can just open in any text editor. You can't edit it, but you can read it. Most of them are readable, right? There are very one or two files where you can write to, but a lot of these files are read-only files. You can only read from them. So you can open it with cat command or a pager and you can read them. You can use any kind of text viewer. You can see that in a very textual format, it shows all the details that you want to know about a process. The name of the process UMAS, the state of the process, the thread group ID, node group ID, pre-ID, parent process ID, tracer PID. What are all these things? It's a topic for another video or maybe another class when I talk about process management and scheduling. But I'm just summarizing information that you can get from here. Some useful utility I can build simply using shell is I can find out the memory usage of this process. To do that, I can try this out. I can just do a grep. Show me all lines that start with capital V, small m from /proc/4809/states. This is the complete memory statistics for this process. What's the peak virtual memory that the process is allocated? What is the current virtual memory usage? How much of physical memory is being used by the process? That's VM RSS, by the way. How much is used for data segments? That's VM data. and how much is used for the process stack, that's 132 kilobyte. So all the details that you find related to memory usage is here. You can also look up the process memory maps. You can find out what files the process opened, how much of disk I was incurred by the process, all possible details. CPU utilization, memory utilization, all kinds of resource usage of the process is tracked by /process PID folder. And this is what all the process monitoring tools would use to gather details about any process. And now we can see that tooling or building applications or tools on Linux is not very complicated. You don't have to remember thousands of functions. You just need to know about thousands of files. Rather, it's easy to locate files and figure out what they do than remembering 1,000 functions. Right? So this is a very interesting thing. And this is what makes Linux kernel rely on a lean API, very few system calls, but a fat ABI, a large number of kernel resources exposed as files and folders. Now, not just this proc file system, there are many pseudo file systems on Linux. You can find out what all file systems are available on Linux currently by looking up this file /proc/file systems. This particular file, again, it's a file that I showed you in the /proc folder. The Linux kernel maintains something called as a file system structure, which is like a linked list. More or less, you can think of it like a linked list. Every file system driver registers itself into that linked list by using registered file system API. I oversimplified the concept, but yeah, this is what it is at a very, very high level. So you have this FS structures or file system structures which are connected in a linked list, and every file system driver is a new link in that linked list. And each link will have a name, and they might have some other details. The important things are exposed in this file. So this is a sysfs file system driver, registered, an entry for it, tempfs, bdev, proc, cgroup, cgroup2, CPU set, dev tempfs, bin fmtm, miscellaneous, configfs, debugfs, you see a variety of them. In fact, you can see the first field, it shows us no dev in the beginning. All these are file system drivers that you see here, which are pseudo file system drivers. They represent pseudo file system. That means that they do not really represent data stored on disk, large part of it. There could be some exclusions like AutoFS and Fuse, which might be a little different, but majority of them, which you see from the kernel's perspective, these are registered as pseudo file systems. The file system that represent persistent data on storage, these are the ones that you see here. I built a very few file system support in this kernel, so you see a very small subset here. But on a real Linux, you will see things like vfat or exfat and ntfs3 and so on, depending on what all devices you're mounted, right? So they are all storage-backed file systems, right? That means they represent data on a storage device. The storage-backed file systems, these are exe2, exe3, exe2, and ext4. And I think I also built a file system driver for reading CD-ROMs, which is ISO 9660. That's a ISO format for CD-ROMs and a couple of DVDs. So the details of them are here. As you can see, there are more number of pseudo file systems on this Linux kernel, which I built, which means a lot of so-called files are managed by these file system drivers with callbacks. When you try opening a file, a particular callback handler is called instead, and that callback handler will populate get some structure details and then create a file descriptor. When you try reading from that file, the read callback handler is called through that file descriptor, and that callback handler will gather all the statistics. If it's like a file like meminfo, the memory statistics are brought in at that moment and then written onto user space. Some of you might even think that when I read a file like /proc meminfo, you might think that this data is there somewhere. In reality, it does not exist anywhere. The data that you see here is generated on the fly. On the fly. In fact, in software engineering, we call this as a generator pattern in design patterns, right? So what is a generator pattern? If I try opening this file called /proc/meminfo, it goes to multiple layers in the kernel. It comes from the syscall interface. Syscall interface go to the VFS layer, which is called virtual file system. The virtual file system layer will now figure out you're trying to open a file in /proc. So it goes to proc file system drivers implementation, and that will have its own open callback. And that open callback will go and check whether there's a link in a specific linked list it maintains. It's called proc dir entry linked list. It checks whether there's an entry called, meminfo. It finds an entry for meminfo, then it just says all good, allocates a file descriptor, and in that file descriptor structure, it maps the file operations to a specific set of callbacks, file operation structure. And then a file descriptor number is sent to the user space. Again, the file descriptor number is an index of an array called a file descriptor table array maintained on a per process basis. That index is what you get. Maybe you get an index 3, file descriptor number 3. And now when you try to do a read on that file descriptor from user land, when you do a read of fd, comma, buffer, comma, whatever size count, right? Let's say 8 kilobyte or something. It all the way goes to VFS. Goes to the kernel from the syscall interface to VFS. VFS calls VFS read. VFS read will figure out from that file descriptor number what is the appropriate file descriptor structure in the kernel from the FD table. And then it calls the reads callback handler, the file operation. The reads callback handler would be registered by the proc file system driver with a name called proc reg read. That's what I've seen. It's called proc regular file read. And that callback handler will figure out that, oh, you're trying to read from a file by name meminfo. That particular link will have a proc dir entry. In that, there's a read callback handler registered by the memory management subsystem. And the memory management subsystem might be having a function. I'm making this name up, but a name could be something different. We need to look up the kernel sources. They keep changing. Let's call it meminfo read. And that function from the memory management subsystem, the meminfo read, will gather the memory statistics at that moment. It gathers the memory statistics at that moment, and then it writes the data that it gathered at that moment onto the user space buffer. That means this data got generated on the fly when you attempted to read this file. And the user space thinks, I got data, I got to open a file, I got data, and that's it. So that is an abstraction, a very clean abstraction that the kernel provides to user space. As an example, all pseudo file systems follow a very similar pattern. Even when I work with the GPIO interface via /sys class GPIO to work with these GPIO pins on my Raspberry Pi board, they pretty much work the same way. There are callbacks being registered for open, read, write, close, and those callbacks control the device in this case, or get data from the device and give you some, write the data onto user space buffer. And this is what application binary interface is all about. Just to summarize now, if I look up the single page presentation, which I just showed you some time back, which is here. So on Linux, a file is a user space ABI abstraction to a kernel managed resource. I repeated it. Now you know what it means. Explained it all over, right? And I also told you most devices that is exposed to user space are done so as special files, mostly device files, or a few devices might give you a sysfs interface. Even if you have a laptop battery and you're running Linux and you see a battery status applet at the beginning of the top of your desktop, you might find it. My desktop taskbar is not shown, but you'll see a taskbar on top on GNOME desktop or KDE or any kind of Linux desktop where you see a battery status applet there, which shows what's the battery status. Where does it get the details? By looking up sysfs. Next time you can just go and check. You can look up sys class, power supply, battery, bat0. Look up that folder. You'll find those details. They're all text files, again, by the way, right? So that means that every kernel managed resource are exposed to user space as special files or files in the pseudo file system. Various kernel subsystems expose their statistics and diagnostics features as files in a pseudo file system. And Linux hosts pseudo file systems by which various kernel subsystems are exposed as ABI. That's all there is to know. So if you're going to be writing a device driver, maybe tomorrow you want to be a device driver developer, here's what you should keep in your mind. If you want to expose this device to user space, so user space applications can communicate to the device or send or receive data on the device. The best way you should do that is by exposing it as a file. Even if you're working on some kernel subsystems, you're building your own kernel subsystem for some use case, and you believe that the subsystem must expose some details to user space, don't try to create new system calls. check whether you can do it with ABI, an ABI abstraction. Last but not least, talking about the Raspberry Pi demonstration I showed you some time back, I talked about sysfs file system. Well, that works on older versions of Linux. If you're using modern Linuxes on a Raspberry Pi board, especially if you're using any recent kernel from 6.5 onwards, they have deprecated that. I guess it's even removed. Now, it's now an obsolete feature. So how do you work with GPIO pins now? The problem with working with GPIO with ABI, I'll tell you the problem in here, which is inherent, is for every GPIO pin, you have a folder, which you export via writing a pin number, right? We write a pin number to export file, and then you get a folder accessible to user space. And in that folder, you have many files. You have to fiddle with all these files. You have to write to this file, you have to read from this file, and so on. So when you work with many GPIO interfaces, your code in user space can get a little too clumsy. And matching, synchronization, and all the things can be a problem. To address this problem, back in 2015, the kernel developers, the maintainers for GPIO subsystem, they proposed an alternative approach, just exposing a single device file. And that file is actually seen today as a proper device file. GPIO is a device. Ideally, it must be shown as a device file, right? But they didn't think about it earlier because of the complexity in ways you can manage GPIO. So they came out with sysfs and provided individual files and let the user space carry the burden of figuring out what files to manipulate at what time. And now, if you look at the latest versions of Linux, even this version also, you still have that interface. It's a 2015 feature. It's there as an alternative way to access GPIO devices. You look up /dev/GPIO chip. You have two files, GPIO chip 0, chip 1, and they have GPIO mem, which gives you access to all the GPIO controller registers. From user space, you'll be able to just open this file and write directly to the GPIO controller registers or read them. So it'll be more faster rather than doing too many open read write calls. You can just open one file and start working on it. And plus, you also have the benefit of using ioctls because it's a proper device file. These are all device files. Oh, okay. I think the GPIO start there. Sorry. Yeah. When you see a small c in the beginning, when you see ls-l listing, it's a character device file. If you see a small b, it's a block device file. These are called as character special files or block special files. The differences between them, I'll talk about it in another video, but I'm just giving you an insight about these. So this is how it is done. And in fact, you no longer can use your good old echo command now, because these files expect you to write binary data or read binary data, which means just like these /dev input event files, where I wrote a C program or use a library, I need to do the same thing in here. Good news is there's a libgpio library available officially by the kernel maintainers for GPIO. They have also provided the user space library. And if you're on a Raspberry Pi, I think there is a wiring pi library, libwiring pi it's called as, and you can use that to make it more easier to work on Raspberry Pi boards using simple functions. And there's a tool, in fact, that uses it, which I can show you. I'll run a trace again on this. Let me go back to my root home directory. I can say trace, and there's a, first let me run this too. It's called, on a Raspberry Pi, it's called as Raspi GPIO. This tool provides a simple interface from the command line to control GPIO bits. Rather than running a lot of echo commands and so on, you can just directly say Raspi GPIO get 20 or get 2021, or you can say set a value for a pin. So all this can be done with simple command line operations. And the way they work is, let me try doing this. Let me try to run Raspi GPIO set 17 and IP. Set this as input pin. Oh no, I made an output pin. That's the output. Set as an output pin. But I'll run a trace on this. As you can see, it opens this particular file /dev GPIO mem for read write mode, and then it sort of creates a memory map out of it. By using a map system call, it sort of maps into the user space. You get access to the GPIO controller registers, and directly from user space, you can communicate. The advantage of using this facility, you can have more real-time IO from user space. That means you can communicate user space without going through complex kernel code path like open, re, callback, and so on, right? The code path is reduced. The device is exposed. You can directly write to a device from user line, and that's a benefit. It's more faster to work this way, and lets you build a lot of features and functionality, like implementing support for things like, say, PCM support, or anything like, implementing all this, also, also, okay, yeah, PCM support and all these things can be done fully in user space rather than relying on kernel facility, right? So that's a benefit that you see here. So anyway, this is a trend change, but yeah, you will still see there's a file, but how you are communicating with the file is not really textual data anymore, but you work with binary. But still, this is an ABI, an application binary interface. Just that it requires a plumbing library, which provides API in the user space itself, and that library will actually communicate to this device to get the job done. Just like the lib input event library, which is there, right? Anyway, so this finishes my video. So I gave you a detailed insight on everything is a file paradigm and why it is a very big deal on Linux kernel design and kernel architecture. And you'll see it cropping up all over the place on Linux, right? So if you're a driver developer or a kernel subsystem developer, this is a concept that you should know very well ingrained. So you're building some subsystem which needs to be exposed into the space, you should make the right call on when you should use APIs that you want to expose or when you should use ABIs. If it's a resource that you're exposing, always use ABI. There are different varieties of ways to do it, but this is how it is. I'll end this video at this moment. So thank you very much. So meet you in the next one. Thank you.